Evolu- Evolution of the Samsung's Exynos CPU microarchitecture. The Samsung, the Exynos family of cores and high-performance big processors developed in a Samsung Austin Research and Design Center (SARC) starting in late 2011. This paper discussed the selected aspect of the microarchitecture of these cores, specifically perception-based branch prediction, spectre, video security enhancement, micro-operation cache algorithms, prefetcher advancement, and memory latency optimization. Each microarchitecture items evolves over time, and both as part of the continuous real improvement and in reaction to the changing mobile workload. In these terms, microprocessor, superscalar, branch prediction, and prefetching. Introduction. Samsung started its development of the Exynos family of the core beginning in the late 2011 with the first generation core M1 supporting a newly introduced ARM v6 64-bit architecture. Several generations of the Exynos M3 CPU, and here referred to as an M1 through the M6, are found most commonly in the Samsung Exynos-based Galaxy S7 through the S20 smartphone and are implemented a variety of process modes from 14 nanometers to 7 nanometers. The core supported the ARM v6 instruction set architecture, both ARC32 and ARC64 variants. The cores superscale a lot of older designs capable of up to 2.9 GHz and employ up to the 3 levels of cache hierarchy in a multiple load cluster. Each Exynos M-series CPU cluster is complemented by the ARM Core Tex A-series cluster in a big little configures in the generation 1 through 3 and 1 through 3 and the big medium little configuration of subsequent generations. Among the numerous details from this effort, this paper selectively covers early evolution of prototyped core microarchitecture M1 through the M5 and future work M6, and adaptation of the microarchitecture to the changes in mobile workloads. And the deep technical details with the microarchitecture. The remainder of this paper discusses several aspects of the front-end microarchitecture, including branch prediction, microarchitecture, security mitigation, and instruction supply, as well as the details of the memory subsystem and the instruction supply, and as well as the details of the memory subsystem, in particular with respect to the prefetching and DRAM latency optimization, so that the overall generational impact of these and other changes is presented in a cross-workload view of IPC. Chapter 2 is methodology. A simulated ledger to shown as here, as well as the internal microarchitecture tuning work are based on the trust-driven cycle, a key performance model that reflects all 6 of the implementation of this paper, rather than a silicon comparison because the M5 and M6 silicon were not available during the creation of this paper. The workload is comprised of the 4,026 traces gathered from multiple CPU-based suites such as the SPEC CPU 2000 and the SPEC CPU 2006. Websuite including the Speedometer and the Octane and the Bbench and some Spider, mobile suite for Agile Antutu and Geekbench and popular mobile games and web applications. SimPoint and relocate calculations are used to reduce the simple simulation runtime for most workloads, and with a volume of 10 billion instructions and detailed simulation of the subsequent 100 mega instructions. Note that the same set of the workloads is utilized here across all of the generations. Some of the more recent workloads did not exist during the development of M1, and some early workloads may have become somewhat obsolete by M6. By keeping the workload suit constant allows a fair cross-generational comparison. Chapter 3 Microarchitecture Overview. Several of the key microarchitecture features of the M1 through the M6 cores are shown in Table 1. Although the cores were prototyped at different frequencies, performance research in this paper comes from a simulation when all cores were at 2.6 GHz, so that the per cycle comparison, IPC, load latencies are valid to compare. Selected portion of the microarchitecture are then uncovered, whereas we will briefly discuss in this section. Full data transformation operation, M3 and later cores contain a faster level 1.5 data TLBs to provide additional capacity and much lower latency than the much larger L2 TLB. Note that according to the table, where there are no significant resource changes from the M1 to M1 to from M1 to M1 to M2. However, there were several efficiency improvements, including the number of deeper queues not shown in table 1, and resulted into the M2 speedups shown later in this paper. Both the integer and floating point register files utilize the physical register file PRF approach for register naming, and M3 and the newer cores implemented cycle integer register and register and moved by the renaming, rewrapping, and referencing counting. And M4 core beyond the have the load and load scaling as feature and the load of the where a load cannot forward its result to the subsequent load a score earlier than usual, so giving the first load an efficient latency over 3 cycles. In general, most resources are increased in size in succeeding generation, but there are several points where sizes were reduced due to the involving trade-off. The examples are M3 the reduction in L2 size due to the change from the shared to privileged L2 as well as the addition of the L3, and M4 the reduction in L3 size due to the changing from the 4-core cluster to a 2-core cluster. 4. The branch prediction. The Samsung Dynamic branch prediction research is rooted in the scaled hashed perceptron SHP approach, advancing the state-of-the-art perceptron predictor over multiple generations. The prediction hardware uses a branch target buffer BTB approach, across both smaller, zeroable taken micro BTB, micro BTB, with a local history hashed perceptron LHP, and the larger 1-2 bubble taken main MTB in MTB with the full HHP. The hardware retains learned information level 2 BTB, L2 BTB, and the virtual address-based BTB, VBTB, in cases of the dense branch lines that are still normal BTB capacity. Function returns are predicted with a return address stack, RAS, with a standard mechanism to repair the multiple speculative pushes and pops. A. Initial redirection. The initial branch predictor design has two performance goals: use a state-of-the-art condition predictor to reduce MPKI and support up to the predictor per clock for the common case of the leading not taken branch, the latter avoiding incurring an extra cycle for or more or many of the not taken branches. For workload discussed here, and the lead branch is taken in the 15% of all cases. The second pair branch taken 24% of all cases, and the two additional sequential not taken 16% of all cases. The first generation SHP consists of 8 tables of 1024 weight cache in sign magnitude representation, along with a local bias weight cap into the BTB entering for each branch. So each of the SHP weight tables is including using the exclusive or hash composed of 3 items. A hash of the global history gives the pattern in a given interval for the table, and the gives records the outcome of the conditional branch as 1 bit. A hash of the path history phase is in a given interval for the table. The phase records 3 bits, 2 through 4, and each branch addressed and countered. A hash of the program counter PC for the branch being predicted. The gift and feast intervals were determined empirically using a stochastic search algorithm, taking into consideration both the diminishing return of the longer the gift shown in the figure in 1 using the publicly available CP5 workloads, and the cost of the maintaining the gift state, and the M1 utilized the 1 in 65 bit gives length in an 80-bit fixed length. To compute the SH prediction, signed bias weight in BTB entries doubled and added the sum of the signed weight to read out of each of the 8 tables according to the hashed history interval. After returning sum is listed, 0 and the branch is predicted taken, otherwise is predicted not taken. The predictor is updated on a misprediction or incorrect prediction where the absolute value of the sum failed to exceed the threshold trained using the threshold training algorithm from a 0 del predictor. To update the SHP predictor, the counters used during the prediction are incremented if the branch was taken, or decremented otherwise, saturating at the maximum or minimum counter values. Already taken branches, both unconditional branches and conditional branches, have already been taken so far. Do not update the SHP weight tables to reduce the impact of the aliasing. The main BTBs are organized into 8 sequential discovered branches per 128 byte cache line, as seen in Figure 2, based on the gross average of 5 instructions per branch. As mentioned above, the additional dense branches exceeding the first 8 built to the virtually indexed VBTB shown in the right of Figure 2 at additional access latency cost. Indirect range predictor is based on the program counter VPC predictor. VPC breaks up the indirect prediction into sequence of unconditional prediction of the virtual pieces that consult SHP with a unique target up to a design-specific maximum chain stored in the BTB at the pre-programmed order of the indirect branch. Figure 3 shows the VPC algorithm with a maximum of 16 targets per indirect branch, several of which are stored in shared VBTB. So, B. First refinement during the M1 design. During early discussion, the 2 bubble penalty on the taken branches were clearly identified as limiting at certain scenarios such as tip loops or code small basic clocks and predictable branches. The baseline predictor is therefore augmented in a micro BTB micro that has a 0 bubble throughput but limited capacity. This predictor is graph-based, specifically using an algorithm to the first filter and identify common branches as common root or a seed, then a learn both taken and not taken etch into graph across several iterations. As seen in the example in Figure 4. Difficult to predict branch nodes are augmented with a loose use of a local history hashed perceptron (LHP). When a small kernel is confined and both fully and fitting within the micro BTB and predictable by the micro BTB, and the micro BTB will lock and drive the pipe at 0 throughput and using until a misprediction. With the prediction checked by the micro BTB and SHP, extremely highly confident prediction will further clock gate the MTB and for large power savings, disabling SHP completely. The above description completes an overview of a branch prediction hardware in the M1. First branch core and the MT core made no significant changes to branch prediction. C. M3 branch prediction throughput. For the M3 implementation, the last of the core was undergoing a significant widening of the pipe, 4 wide and 6 wide of throughput, as well as more than a doubling of the out-of-order window. To maintain the ability to feed a wider and more capable microarchitecture, the branch predictor needed to be improved. To reduce the average branch turnaround, the micro BTB graph size doubled and reduced the area increased by the only adding the entries that could be used exclusively to more unconditional branches. For workloads that could not fit within the micro BTB, the concept of an early already taken redirect was added for the MBTB. Already taken branch will redirect a cycle earlier. Such branches are called 180 branches, for short 1 bubble already taken branches. M3 also made several changes to further reduce MPKI In predictor, doubling of the SHP rows, reducing the aliasing for conditional branches, and doubling of L2 BTB capacity. The M4 branching prediction changes focus on the large workloads. The M4 generation predictor refinement focused on the better support for large working exercise. So the L2 MTB was doubled again, making this generation capable of holding 4 times as many branches as the first generation. In addition, the L2 BTB fails into BTB has their latency slightly reduced and their bandwidth improved by 2 times, emphasizing the importance of the real use case code. This capacity and the latency bandwidth change significantly improve the performance of the mobile workloads like B-Bench by 2.8% in isolation. M5 M5 branch prediction efficiency improvement. For the M5 generation, the branch predict research for focus on improving the predictor in terms of several different efficiencies. Some sections of the code are very branch sparse, sometimes with the entire BTB lines devoid of any actual discovered branches. Thus, the design added the state to the track empty line optimizations, skip an entire line devoid of branches to reduce both the latency and power of looking up the uninteresting addresses. The previous generation had already accelerated always taken branches via one bubble to redirect. In this generation, this idea was extended to a different way, reducing the bubble to a zero via replication and expanding the coverage. Often taken the branches, the replication is done to copying the targets of the array, taking the branches into their predecessor's branches MTB information, thus providing zero bubbled always taken Z and the zero bubble often taken GOT and prediction capability. Thus, did on BTB look up for the branch and avoid both target and is taken the target location led next to the candidate of always often taken branch, the target of that subsequent branch. This increased the storage cost, but greatly improved the taken branch throughput, as shown in the example in Figure 5. And Figure 5 is increasing the branch throughput by the reducing bubbles for already taken AT and the zero often taken GOT predictions. The replication schemes allows X to specify the redirect both A to B and the target of the next branch after address A. With a new zero bubble structure in MBTB and micro BTB, and this GAT and GOT predictor can sometimes contend. The main predictor has no startup penalty, but uses full MTB and SHP resources, while the micro BTB has 2-cycle startup penalty, but can chain the zero bubble prediction without read branches and could also save the MBTB and SHP power on TK corners. A heuristic arbiter is used to intelligently select the zero bubble predictor to use. Given the growing capability on the one bubble predictors, and 5 design was to integrate the area micro BTB by reducing number of entries. Having the GAT and GOT predictor participate more, this results in a better area efficiency for a given amount of the performance. So the SHP increased from 8 tables to 16 tables of the 2048 8-bit weight in a sign magnitude representation, reduced NKKB both alias in reductions as well as increasing the number of the unique tables. The gist length of the words increased by the 25% and the table hash intervals rebalanced for this longer gist. Finally, one performance problem was effective refill time for after previous predict. If the correct path contained several small basic blocks connected to taken branches, it could take many cycles to refill the pipe, which was observed in some of the key web workloads, among others. This is shown in Figure 6, where we assume the basic block A and 5 instructions, and basic block B and B has 6 and basic block C has 3, and all ended with the taken branch. And once a pre-mispredicted signal to branch prediction pipe start fetching at the correct target A, and in subsequent cycles predict sequential fall through within a fetch with the 6 at address A plus 6 and A plus 12. After mispredicted micro BTB disabled until the next seed branch. However, when a branch prediction pipe reaches in the third stage, it says that A has predicted target taken branch to B, and consequences in the speculative prediction lookups for A plus B, A plus 6, and A plus 12, and the restart the branch prediction pipe for the address B. In this example, assume the A basic block contains 5 instructions. If the B has a small basic block has taken branch, it again required 3 cycles to fetch an additional 6 instructions. All told in this example, and the return requires 9 cycles from the mispredicted redirect to fetch 14 instructions, and the downstream core will likely become the fetch served. Figure 6 illustration of the slow effective refill time after we split it to a series of small basic blocks. In order to help mitigate this long effective refill time for after mispredict, M5 core added a block called a mispredicted recovery buffer LRB. After identifying the low confidence branches, it allows the highest probability sequence of the next 3 patchy addresses on a matching mispredicted redirect, and the predicted fetch addresses can be read sequentially out of the MRB in consecutive cycles as shown in figure 7, eliminating the usual branch prediction delay in this example, allowing 14 instructions to be avoided in only 5 cycles. Note that the third page's MRB predicted target address is checked against the newly predicted target from the branch predictor, and if they agree, the correction is needed. The F. Section F, the M6 branch prediction in direct capacity improvement. For the sixth generation, the greatest adjustment was to respond to a change in popular languages and programming styles in the market. The first of these changes were to increase the size of MTB by 15% due to larger working set sizes. Second, JavaScript increased the use to put more pressure on an indirect target, allocating in some cases 100 of a unique indirect target for a given indirect branch via function calls. Unfortunately, the VPC algorithm required ON cycles to train, and predict all virtual branches for an n-target indirect branch. It also consumed much of the VTB for such many target indirect branches. So the solution to the large target count problems is a dedicated unique storage for branches with a very large target possibility. A trade-off the VPC algorithm is retained since the accuracy of the SHP VPC hash table lookups still proved superior to a hash table lookup for a small number of targets. Additionally, large dedicated storage take a few cycles to access, and so doing a limited length of the VPC in parallel with a bunch of the hash table lookup proved to be a superior throughput and performance. The hybrid approach is shown in figure 8 and reduced end-to-end prediction latency compared to the full VPC approach. Figure 7 is a predicted recovery buffer MRB, providing the highest probability page block addresses after identified low confidence mispredicted branches. Figure 8 is the VPC reduction to a 5 target followed by an indirect hash. Performance modeling shows data accessing the hash table lookup indirect target table with the standard SHP GIST, FIST, PC hash did not perform well, as the precursor conditional branches do not highly correlated with the indirect target. A different hash is used for this table based on the history of recent indirect branch targets. G. Overall impact. From M1 and M3, M6, the total of the big budget for branch prediction increased greatly, in part due to challenges of the predicting web workloads on their much larger working set. Table 2, it shows the total of the big budget for SHP, L1, and L2 branch predictor structures. The L2 BTB uses a slower, denser macro as part of the latency era trade-off. Table 2. Branch predictor storage in kilobytes. With all of the above challenges, the predictor was able to go from an average predicted per 1,000 instruction MPKI of the 3.6.3.62 for a set of several thousand workload slices on the first implementation to an MPKI of the 2.45 2.54 for the latest implementation. This is shown graphically in Figure 9, where the breadth of the impact can be bold clearly. On the left side of the graph, many of the workloads are highly predictably and unaffected further improvement. In the middle of the graph are interesting workloads, like most SPEC into and Geekbench, where better predictor schemes and more resources have a noticeable impact on reducing MPKI. On the right are their workloads with very hard to predict branches. The graph has the y-axis clipped to the highlighted bulk of the workload, which have the characteristics of an MPKI under 20. But even clip a highly predictable workload M1 improved by the 12% on subsequent generations. Overall, these changes reduced suspectly into 2006 and the MPKI by the 25.6 from the M1 to M6. Chapter 5. The Branch Prediction Security. During the evolution of the microarchitectures discussed here, several security vulnerabilities, including the Spectre, becoming the concerning the several features were added to mitigate the security holes. In this paper's discussion, the model is based on the fully trustworthy operating system and a hypervisor present. The untrusted user-landed program and the visual user-landed programs can create arbitrary code, whether from the having full access or from ROP widget programming. This paper only discussed on the features to use the hardened, interactive, and return stack prediction. Simple options such as erasing or branch prediction stayed on context switching as may be necessary in some context transition, but come at the cost of having to retrain when going back to the original context. Separating storage per context and tagging entries by context come at significant error cost. The compromise solution discussed next provide improved security with minimum performance and timing and area impact. Figure 9 is MPKI and across the 4026 workload slices. Y-axis is clipped and 20 MPKI for clarity. Note that the M2, which has no substantial branch prediction changes over M1, is not shown in this graph. Provide improved security with minimal performance and timing, and the new front-end mechanism hashed per context state and scrambled the long instruction address target stored in range predictors branch target buffer BTB or return address stack RAS. So the mixture of the software and hardware controlled entropy sources are used to generate the hash key context hash for a process. The hashing of the stored instruction address target will require the same exact numbers of the perfectly unhashed and unscrambled predicted taken target before redirecting the program address of the CPU. If a current context is used to read structure, the grounded target may be predicted taken but will jump to an unknown predictable address and later mispredicted recovery will be required. The computation of the context hash is shown in figure 10. The context hash register is not a software accessible and contains the hash used for target encryption, decryption, and its value is calculated with several inputs, including a software entropy source selected according to the user, kernel, hypervisor, or firmware level, implemented as a scxtmum_elxr as part of security features CSP2 cache speculation variant 2 described in the ARM version 8.5. A hardware entropy source, again selected according to the user, kernel, supervisor, or firmware level. Another hardware entropy source selected according to the security state. An entropy source from a combination of ASID, process ID, and VM ID, virtual machine ID, and a security issue and a privilege level. Note that the context hash computation is performed completely in hardware with no software visibility to an intermediate value, even to the hypervisor. The computation of the context hash register also include rounds of entropy diffusion, specifically deterministic, reversible, nonlinear transformation to leverage per bit randomness. The small number of the cycles required for the hardware to perform a multiple level job hashing and iterative entropy splitting have a minimal performance impact given the latency of a context switch. Within a particular process context hashes use the very fast stream cipher to the exclusive or whether indirect branch or written target being stored to the BTB or RAS, as in figure 11. Such as a simple cipher can be inserted into RAS and BTB lookup without much impact to the time of paths as compared to a more rigorous encryption and decryption scheme. And to protect against the basic plain text attack, a simple substitution cipher and a bit reversible reversal can further obfuscate the actual store address. When the branch predictor is trained and ready to predict the jump to target from this common structure, the common will be programmed the context hash to perfectly invert and translate out of the correct prediction target. This approach provides prediction against both cross-training and delayed attacks. If one attacker process tried to cross-training an interactive in predictor with a target, it will be descripted the context hashing into a predictor structure and read out and decoded in a victim's execution at a different context hashing, which will be a region in a victim beginning execution at a different address than intended attack target. With regard to the replay attack, if one process is able to infer mapping from the plain text target to the context hash encrypted target, this mapping will change on future execution, which will have a different process context, process ID, and etc. In addition to the operating system can intentionally periodically alter the context hash for the processor or all processes by changing one of the SW entropy and level inputs, for example, and the expense of the interactive mispredict and retraining and provide protection against undesired cross-training during the lifetime of the process, similar to the concept in seizure. Chapter 6 Micro Operation Cache UOC M1 through M4 implementation fetches and decoding instructions as is common in a modern out-of-order pipeline. Fetch instructions from an instruction cache, buffer them into instruction queue, and generate a micro operation through the decoder buffer feeding them to the later pipe stage. As the design moves from the undersupply 4 instructions micro operation per cycle in M1 to 6 per cycle in 3, with future ambitions to grow up to 8 per cycles. Fetch and decode power with significant concern. M5 implementation added to micro's operation cache as an alternative micro operator supply path, primarily to save fetch and decode power and repeatable counters. The UOC can hold up at 384 micro operations provided up to 6 micro operations per cycle to subsequent stages. The view of the instructions by both the front and by the UOC is shown in Figure 12. Figure 12 instruction-based and micro-operation-based views. The front end operates in 1 and 3 different UOC modes. Filter mode where the U micro BTB prediction determines the predictability and size of the code segment. Build mode and where the UOC is allocated the appropriate page block, and fetch mode and where the instruction cache and decode logic are disabled and instruction supply is solely handled by the UOC, and each mode is shown in the flow chart in figure 13 will be described in more detail in the next paragraphs. The filter mode The filter mode is designed to avoid using the UOC build mode when it would not be profitable in terms of both power and performance. In filter mode, the micro BTB predictor checks the several conditions to ensure the current code segment is highly predictable and will also fit within both the micro BTB and the UOC final sources. When the conditions are met, the mechanism switches into build mode. To support the build mode, the micro BTB predictor is augmented with a built bit in each branch's prediction entry, tracking whether or not the target basic block has already been seen in the UOC and back-propagated to the predictor. Initially, all of these built bits are clear, and one of prediction lookup, the build timer is implemented and the build bit is checked. If the build is clear, the build edge is implemented, number of build edges is implemented, and the block is marked for location in the UOC. Next, the UOC tags are also checked. If the basic block is presented, information is propagated back to the micro BTB predictor to update the build bit. This back propagation avoids the latency of the bit tag as check of the prediction time and the expense of the additional build request that will be squeezed by the UOC. As Wilson said, the number of fetch edge is incremented. Is it number? Yes. When the ratio of the patch edge and the build patch reaches the threshold and the build timer has not timed out, it indicates that the code segment should not mostly or completely UOC hit, and the front end shifts into a fetch mode. In fetch mode, the instruction cache and decode logic are disabled, and the micro BTB prediction feed through the UAQ into UOC to supply instruction to the rest of the machine. As long as the micro BTB remains accurate, the BTB is also disabled, saving additional power, while in fetch mode, the front end continuously examine the build hit bit and update the build edge if the bit is clear, and fetch edge if it is set. If the ratio of the number of bit edge to number of fetch edge reaches a different threshold, it indicates that current code is not hitting them sufficiently in the UOC, and the front end shifted back into the filter mode. Chapter 7. L1 data prefetching. The hardware prefetching into L1 cache. Hardware prefetching into L1 cache allows data to be fetched from memory early enough to hide the memory latency from the program. Prefetching is performed based on the information from demand loads and can be limited by size of the cache and maximum outstanding missions. Capacity of this cache grew from the 32 kilobytes in M1 to the 64 kilobytes in M3 and 128 kilobytes in M6. Outstanding missions grew from the 8 in M1 to 12 in M3 to 32 in M4 and 40 in M6. The significant increase in misses M4 was due to the transitioning from a field buffer approach to the data-less memory address buffer (MAB) approach that held field data only in the data cache. A. Algorithm. The L1 prefetcher detected the stride patterns with multiple components. For example, plus 1 times 3 plus 2 times 1, meaning of the stride of the 1 repeated 3 times, followed by a stride of 2 occurring only once. It operates the virtual address space and prefetches are permitted to cross page boundaries. This approach allows a large prefetch degrees. How many outstanding prefetches are allowed to be outstanding at a time? To help cover memory latency and solve prefetcher timeline issues, this design also inherently acts as a simple TLB prefetcher to preload the translation of the next pages prior to the demand access to those pages. The prefetcher trained on a cache methods to effectively use the load pipe bandwidth to avoid noisy behavior and improve the pattern detection. Out of order addresses generated from the multiple load pipes are reordered back into program order using an ROE-like structure. To reduce the size of this reorder buffer, an address filter is used to deallocate duplicate entry to the same cache line. This further helps the training unit to see unique addresses. The prefetcher training unit can train on multiple streamlines simultaneously and detect multi-stride similar to 25. If the same multi-stride pattern is repeated, it can detect a pattern, for example, and consider this access pattern. A8 to A4, A9 to A11, and A13, A18, and so on. This above workload has a stride of +2, +2, +5, +2, +2, +5. The prepatch engine locks on a pattern of +2 times 2 +5 times 1 and generates prefetch 8 +20, 8 +22, and 8 +27, and so on. The load stream from the reorder buffer is further used to confirm the prefetch generation using a confirmation queue. Generated prefetch addresses get and queues into confirmation queue, and subsequent demand memory access will match the confirmation queue. A confident scheme is used based on prefetch confirmations and memory subsystem latency to scale prefetch degree. See next section in more detail. B. Dynamic degree and one pass, two pass. In order to cover the latency to main memory, the required degree can be very large, over 50. This created two problems. One, lack of the missed buffer and the accessed prefetches for short-lived patterns. These access prefetches waste power and bandwidth and cache capacity. A new adaptive and dynamic degree is the mechanism for access prefetches. Prefetches are grouped into windows, and with a new window size equal to the current degree, a newly created string starts with a low degree. After some number of the confirmation in the window, the degree will be increased if there are two confirmations in the window and degree is increased. In addition, in the feed demand stream overtake the prefetch stream, the prefetch issued logic will skip ahead of the demand stream and avoid redundant late prefetches. To register the processor on L1 missed buffers, a two-pass mode schedule is used. Starting with the M1 shown in figure 14. Note that the M3 and beyond added and M3 between the L2 and interconnect. When a prefetch is issued in the first time, it will not allocate the L1 allocated on L1 missed buffer, and but instead be sent to a field request into L2. And the prefetch address will be also inserted into queue, which will hold until sufficient L1 missed buffers are available. And L2 cache will issue the request to the interconnect tree and eventually receive the response 4. When a free L1 missed buffer is available, an L1 missed buffer will allocate 5 and an L1 field request will occur. 6 and 7. The scheme is suboptimal for cases where the working sets fits into the L2, since every first pass prefetcher to the L2 would hit. To counteract this, the mechanism also tracks the number of first prefetch hits in the L2, and if they reach a certain watermark, it will switch into one pass mode. In this mode shown in the right in figure 14, only step 2 is initially performed. When there are available missed buffers, which may be immediately, step 5 and 6 and 7 are performed, saving both power and the L2 bandwidth. C. Special memory streaming prefetcher. The multi-stride prefetcher is excellent at capturing regular access to memory. However, the programs which traverse a linked list or other certain types of data structures are not covered at all. The to attack these cases, M3 and additional M1 prefetch engine is added a special memory stream SMS prefetcher. This engine tracks the primary load the first miss to a region. They attach to associate access to the E and misses within the different PC. When a primary load PC appears again, the prefetches for associated load will be generated based off the remembered offset. Also, this SMS algorithm tracks confidence for each associated demand load, only associated load with high confidence prefetches to filter out the ones that will appear transiently along with the primary load. In addition, when a confidence drops to a lowest level, the mechanism will only issue the first pass L2 prefetch. With two different prefetch engines, the scheme is required to avoid duplicate prefetches, given that a trained multi-thread engine can prefetch further ahead of the demand stream, the SMS engine. Confirmation from the multi-thread engine suppresses the training in the SMS engine. D. Integrated confirmation queues to cover the memory latency and allows multiple load streams to operate simultaneously. The size of the confirmation queues needs to be considerably larger also at the start of the pattern detection. The pre-patch generation can lag behind the stream since the confirmation are based on issued prefetches that can be result in a few confirmation as prefetch degree is a function of confirmation. This mechanism can skip the degree in a low state and prefetches may never get ahead of the demand stream. To combat the above issues, the M3 core introduced an integrated information confirmation scheme to replace the confirmation queue. The new mechanism kept the last confirmed address and used the locked prefetch patterns to generate the next n confirmation addresses into queue, where the n is much wrapped in a frame degree, and this is the same logic as prefetch's logic design, but acted independently. This confirmation scheme reduces the confirmation structure size considerably and also allows confirmation even when a prefetch engine has not yet generated a prefetch. The Section 8. Large cache management and prefetchers. Over 6 generations, the large cache alternative hierarchy involved as shown in Table 3 below. M3 added a large but more complex 3-level hierarchy, which helps balance latency versus capacity objectives with the increasing working set needs of the modern workload. A. Coordinated cache hierarchy management. To avoid data duplication, the outer cache levels L3 are made exclusive to the inner caches L1 and L2. Conventionally exclusive caches do not keep the track of data reuse since the cache lines are sorted back to the inner level caches. The L2 cache tracks both latency and hits within the L2 as well as subsequently relocated from the L3 cache. Upon the L2 cache out, these details are used to intelligently choose to either locate the cast out into L3 into elevated replacement state or an ordinary replacement state, or avoid the location altogether. This bidirectional coordination allows the cache to preserve the useful data in the wake of the transient stream or when the application working set exceeds the total cache capacity. Amongst the hardware override, each cache text or some metadata to indicate the use or data behavior of the associated lines and following different transitional types, prefetch versus demand. The metadata is passed through the request or responder channels between the cache level. There are some caches that are needed to filter out of being marked as usually used, such as the second pass prefetch or the two pass prefetching. More information can be found in the related patent. The B. Body cache prefetcher. The L2 cache tags are sectored at a 128 byte granular for a default data line size of the 64 byte. This sectoring reduces the tag area and allows lower latency for tag lookup. Starting in the M4, a simply body prefetcher is added at every demand miss to generate a prefetcher for each 64 neighbor body sector. Due to the text sectoring, the disk prefetching does not cause any cache pollution, since the body sector will stay invalid in absence of the body prefetching. There can be an impact on a DRAM bandwidth through if the body prefetches are never accessed. To alleviate that issue, a filter is added to the body prefetcher to track the pattern of the demand accesses. In the case where the access pattern observed almost always skip the neighboring sector, the body prefetching is disabled. C. Standalone cache prefetcher. Starting in M5, standalone prefetcher is added to the prefetch into the low-level caches beyond the L1s. This prefetcher observes the global view of the both introduction and the data accesses at lower cache level to detect streamed patterns. Both demand accesses and core-initiated prefetches are used for training or including the core prefetches to improve the timelines when they are eventually filled into L1. Amongst the challenges of the standard of prefetcher is the out-of-orderness of the program accesses observed at a low level. Caches cannot pollute the pattern is trained. Another challenge is the fact that it operates on physical addresses, which limited each span to a single page. Similar hits in the L1 can filter the access stream seen by the lower level of cache, making it difficult to isolate the real program access stream. For those regions, the standalone the prefetchers uses an algorithm to handle long, complex streams with large training structures and techniques to reuse the running across the 4 KB physical page crossing. The standalone prefetcher also employs a two-level adaptive scheme to maintain the high accuracy of the executive prefetches as explained below. D. Adaptive prefetching. The standalone prefetch is built with an adaptive scheme shown in figure 15 with two modes of prefetching, low confidence mode and high confidence mode. In low confidence mode, phantom prefetch are generated for confidence tracking purposes into a prefetch filter, but not issued to the memory stream or issued very conservatively. The confidence is tracked through the demand accesses matching entries in the prefetching filter. When the confidence is increased beyond a threshold, high confidence mode is entered. In high confidence mode, prefetches are issued aggressively out of the memory system. The high confidence mode relies on a cache metadata to track the prefetch's confidence. This metadata includes the bit associated with the text to mark whether the line was prefetches if it was accessed by a demanded request. If confidence reduced below threshold, the prefetcher transitions back to the low confidence mode. Hence, the prefetcher accuracy is continuously monitored to detect transition between the application phases that are prefetcher friendly and phase that is difficult to prefetch, or when the out of orderness makes it harder to detect the correct pattern. Chapter 9. The Memory Access Latency Optimization. The Exynos mobile processor designs contain three different voltage and frequency domains along with the core path to main memory, the core domain, interconnect domain, and the memory control domain. This provides flexibility with regard to the power usage in different mobile scenario, GPU heavy, core heavy, and etc. However, this required 4 on-die asynchronous crossings to outbound and to inbound, as well as several blocks with buffering along the path over several generations. The Exynos designs add several features to reduce the DRAM latency through multiple levels of the cache hierarchies and interconnect. These features include data fast path bypass, read speculation, and early page activate. The CPU memory systems on M4 supports an additional dedicated data fast path bypass directly from DRAM to the CPU cluster. The data bypasses multiple levels of cache return path and interconnect queuing stage. Also, a single direct asynchronous crossing from the memory controller to the CPU bypasses the interconnected domains to asynchronous crossings. To further optimize latency, the CPU memory system on M5 supports speculative cache lookup bypass for latency critical reads. The read requests are classified as latency critical based on various heuristics from the CPU. For example, demand load, miss an instruction cache, miss table work request, and etc., as well as history-based cache miss predictor. Such reads speculative issue to the coherent interconnect in parallel to checking the text of the levels of cache. The coherent interconnect contains no filter directive that is normally looked after the path of the memory access for coherence management. The speculative read feature utilizes directly lookup to the further predict with a high probability where the requested cache line may be presented in the bypass the lower levels of cache. Vs. Then it cancels the speculative request by informing the requester. This cancel mechanism avoided penalizing memory bandwidth and power on unnecessary accesses, acting as a second chance to correct the predictor in case the cache miss prediction from the first predictor is wrong. The M5 CPU system contains another feature to reduce the memory latency. For latency critical reads in dedicated side-made interconnect, send your early page activate command to the memory controller to the speculative open a new DRAM page. This interface, like the fast data path mechanism described above, also bypasses two asynchronous crossing with one. The page activation command is hint the message controller may ignore under heavy load. Chapter 10 is the overall impact on average load latency. The net impact of all the generational changes on average load latency is shown in figure 16. These include the cache size, prefetching, replacement algorithm, and the DRAM latency changes discussed in the above sections. Note that the three-cycle cascading load latency feature is clearly visible on the left of the graph for workloads that hit in the DL1 cache. It also partially contributes to the lower DL1 cache hit latencies for many other workloads that occasionally miss. There are many other changes not discussed in this paper that also contribute to the lower average low latency. Overall, these changes reduce the average load latency from 14.9 cycles M1 8.3 cycles M6 as shown in figure table 4. Chapter 11 Conclusion. This paper discussed the evolution of branch predictor implementation, security prediction, and prefetching improvement, and memory latency reduction. These changes, as well as dozens of the other features throughout the microarchitecture, result in a substantial year-on-year frequency neutral performance improvement. Throughout the latent of the Exynos course, the focus was to improve the performance across all types of workloads, as shown in figure 17. Low IPC workloads were greatly improved by the more sophisticated coordinated prefetching as well as the cache replacement victimized optimization. Medium IPC workloads benefited from the MPKI reduction, cache improvement, additional resources, and other performance tweaks. A high IPC workloads were kept by the M1's 4 wide design. M3 and beyond were augmented in terms of width and associated resources needed to achieve 6 IPC for workloads capable of that level of the parallelism. The average IPC across these workloads for M1 is 0.6, while the average IPC for M6 is 2.71, which showcases a compounded growth rate of 20.6% frequency neutral IPC improvement every year. Acknowledgement team. Thank you. Today I read this paper, The Evolution of the Samsung Exynos CPU Microarchitecture Industrial Project, from the industry track of the ISCA 2020 program. Thank you for your time. See you next time.